All right, so first question. And on this test review, you're going to see little headings that kind of help you understand the context of the group of questions. So the question, can you hear me now, okay, is telling you that the next section of questions are based around sound and that type of stuff. So I stand outside of the road near Red Cap. I can often hear the sirens as the fire department responds to an emergency. Don't ask why I spend so much time standing on the side of the road. I sometimes just need to go for a run and clear my head. And if I get tired because I am an old man with creaky joints, that is no reason to shame me. I am out here living my best life. Anyways, if the siren has been tuned to produce a sound with a frequency of 1670 hertz, what frequency will I hear when the truck is traveling 13 meters per second away from me? So right away, I see this stuff. I'm thinking this is Doppler effect, okay? And we can remember from our work that the Doppler effect equation says that the new frequency will equal the old frequency times the velocity of sound plus or minus the velocity of the, is it the observer or is it the source that goes on top?
Observer.
Are you guessing or are we sure?
I'm sure, but I just...
See, this is what matters,
Really
right? We're rattling this stuff off. Obviously, either having a formula sheet that you look at or into the textbook. These are all part of the process.
So the bottom is source, so I know the top is observer.
You know the top is the source?
No, bottom is source.
Bottom is the source.
I can read that one.
Okay. So, the top should say OBS then on your formula, which stands for the observer,
Yeah.
and source is SND. Or not, sorry, SOURCE. There we go. Source. Let me zoom in here a little bit. Is that a little bit easier for those of you trying to read the board? Okay, so we've got, this is the structure formula. Whenever we have a Doppler effect question, we know it's a Doppler effect question because we're talking about frequencies and the velocity of things traveling, whether it's an individual listener or the source of the sound. Okay, so jumping back into the question, the 1670 hertz frequency is the sound produced by the truck, which means that's the initial frequency, not the new frequency. So in our equation, we have F prime will equal 1670 times, what's the velocity of sound on Earth, in the air, traveling from a truck to me? 343. It is 343. That's in the textbook on page 323, if you need to look it up. Plus or minus the velocity of the observer. So me on the side of the road, am I running or am I standing still? I'm standing still. And so we're going to use a 0 up on top. And then on the bottom, we've got our 343 again, minus or plus. And the velocity of the source, the truck is traveling 13 meters per second away from me. With the plus or minus signs, remember that if you expect the frequency to go up, you expect a higher frequency because of the Doppler effect, you should use the top signs. If you expect the frequency to go down, you should be using the lower signs. So as the fire engine goes away from me, is it the or the which one is it? Yeah, you guys aren't going to reproduce it. It's the sound as it drops in pitch. So we expect a low frequency, which means we're going to use the lower signs. On top, it doesn't matter. We still have our 350 or 343, but on bottom, we're going to use 343 plus the 13. So with my calculator on pretty simple calculation, I'm going to do that bottom first. It's 343 plus the 13. And then I'm going to go 343 divided by that 356, and times it by my 1670 to get a new frequency of 1609. 1609 hertz. That would be my new frequency. Any questions?
So if it was coming towards you, you would use
Yeah, you'd use the upper signs if the distance is closing. You use the lower sign if the distance is growing. In Greece, he spent a year in silence just to better understand the sound of a whisper. That's from A Knight's Tale. It's a good line relative to sound stuff. Anyway, yes?
And
Go ahead.
can be moving during.
Yeah, so the observer or the source can be moving. In this class, we're not going to give you both. We're going to put one of them stationary. So you should have 1 0 and 1 known value. Okay, so after a year in silence, even the sounds of 67 decibels can cause irritation to my perfectly sensitive ears. I have 3 speakers set up with a sound level of 60 decibels each. If I turn on all 3 speakers, what will the sound level be? And is that going to be too loud for my ears? The trick here is to recognize you cannot add decibels to decibels. You can only add intensity to intensity and convert that intensity to decibels. So the first thing that we have to recognize is that sound level is equal to 10 log of I over 10 to the negative 12th. That's my base formula for sound level. If you could tell me the intensity of the 3 speakers, then I could tell you how loud the 3 speakers will be. There's a version of this formula that we worked on and built to go the other direction. Can you dig through your notes and find the formula for what intensity equals in terms of beta? Go ahead.
I equals 10 to the B divided by 10 negative 12. It's weird.
I believe it looks like that.
Yeah.
So it's 10 raised to the beta divided by 10 minus 12. So there's a little calculation in there. If you could tell me your sound level is 60 decibels, that's my beta. Okay? And so to get the intensity of one speaker, okay, that would be 10 raised to the 60 over 10 minus 12. Okay? So what's the intensity of a single speaker? We put that in the calculator. Well, should be 10 raised. 60 divided by 10 is clearly 6 minus 12. I get 1 e negative 6. Okay? That's 1 with 6 decimal places of movement. That would be 1 e negative 6 watts per meter squared. But that is for one speaker. If I'm going to turn on all 3 speakers, what's going to happen to the intensity that's produced? Well, that's going to triple, right? Because 1 times 3, we're going to get 3 times that. So the intensity for 3 speakers will be this number times 3, 1 e negative 6, which is 3 e negative 6 watts per meter squared. Okay? So that's the intensity of 3 speakers. So now I need to take that intensity and turn that into a loudness. How loud is that intensity? So I'm going to bring that information from here. Oops. I'm going to send it over to help find the sound level of 3 speakers, which would be 10 times the log of 3e negative 6 over, okay, when we do 10 to the negative 12, an easy way to write that is 1 e negative 12. Or you can use the exponent and do 10 raised to the negative 12. Don't put 10 e negative 12 because it's 1 times 10 to the negative 12. And so be careful with the way you put that in. But, and I'm just going to do this in small stages. So I'm going to times that by 3 that I should have done earlier. There's my 3 negative 6 divided by 1 e negative 12. And now I need to take the log of that answer and times that by 10. I get 64.77 or 64.8. 64.8 dB. And then the question, is that too loud for my ears? Now I can go up to 67 without problems, so it's fine. Getting there, but it's not a problem. Any questions about intensity and sound level? If you look at the last, when we did the test related to this, it was something like, hey, there's 4 speakers. What's the loudness of 3? So you have to take the 4, break them into 1, and then use the 1 to make a 3, and kind of go back and forth using the fraction idea. But yep. Okay. Okay, the next question is a ray diagram. Now, I built the ray diagram on your sheet with a ruler to kind of get things spaced properly. If you want to know what the spacing was, it's 3 centimeters to the first focal point. 4 is the focal length of this this lens. It is a converging lens because it's skinny on the tips and fat in the middle. You should have ray diagrams to go off of, to practice off of with this. But we're going to draw the 3 rays and show where where the image is going to gather. Now here's the deal. You do not have to use the formula, the 1 over DO plus 1 over DI equals 1 over F. However, if you want to know, did I get this right? Or if you want to know ahead of time, where's it going to land if I do this right? You could make that calculation and determine what the answer is supposed to be before you get into the weeds. All right. So if we pick up drawing our 3 rays, this is going to be a really bad sketch, but bear with me. Okay. First ray is parallel to focus. So we'd come out. Oh, gosh, I hate this. All right. Something like that. And then we draw from there through the far focus. So it looks something like that. Okay? So parallel and then through the far focus. The next one is through the near focus. And then it comes out of the near focus, hits the lens, and comes out parallel. One thing to keep in mind when you're doing this, make sure that you're on the center line when you do all the bending. Don't bend at the surface of the glass. The glass, technically it bends at one surface of the glass, it bends at the second surface of the glass differently, but the net result is bending through the center. So just go to the center line for your rays. And then our third and final ray is always straight through the center of the lens. So it should look something like that. If we do well with it, we're going to get a spot where all of them cross together. And that place where they all cross becomes the image. So that's what I'm looking for. I do want you to draw the image. We can tell right now it's upside down. I could measure how tall it is and see if it's the same height as the original object, or if it's been shrunk or grown, magnified or minimized through the lens. But I want to see all 3 lines come together, and I want to see where you draw that image. Yep.
How do we know that it's flipped? It's just because it's on the bottom?
It's on the bottom, yeah. Okay. To draw, so if you think about it, we left the tip of the arrow, so wherever we gathered has to be the tip of the arrow. And so the rays of light from the tip become the rays of light that lead to the tip. So they must match that way. Any questions about drawing that? Again, if I looked at it from the mathematical perspective, 1 over DO plus 1 over DI equals 1 over F. The object distance would have been 7 DI equals, and the focal length was 4. If I solved this for DI, I would get an image distance, and then I have to know the rules, right? There's a page in the textbook that has the rules in terms of what's positive, what's negative. This one's going to come out positive. meaning it's beyond the lens. And it would come out with a number that would help me understand about how far out this should be. Any questions? Okay. We have light coming in from the sun, and we want to know what theta is. Okay. Just so that we're clear on a couple of things, I always think these questions are kind of set up in a really generic way, but I watch kids who can't seem to grasp where the boundary line is. That really throws them off. They also have a hard time figuring out where's the light coming from versus going to. It technically doesn't matter where it's coming and going, but let's say this. If there's water here and there's glass here, I think it's fair to say that this must be the surface between the two. I don't know why, but some people go in and draw it the other way. Find the two materials. Wherever the line between those two materials is, that's your boundary. When we do these calculations, this is a Snell's law problem, we always make sure that we measure to the perpendicular to the surface. So this angle here is garbage. I don't want it. It's throwaway. I don't need it. I want this angle, and I want this angle. Okay, these are the two angles that I'm going to work with because they are perpendicular to the surface, is what we're measuring from. Snell's law says n1 sine of theta 1 equals n2 sine of theta 2. Doesn't really matter which one's 1 and which one's 2, but you could imagine it's, I don't know, it could be coming from the glass side to the water or the water to the glass. It won't matter. N1, let's just call that water. What's the index of refraction or N value for water? Well, if you don't know, it's a page number. Does anyone remember what it is? It's like the most commonly used one.
Page 642?
Sounds about right. Should be 1.33. Sine of the angle on that side is 32 equals. Then I've got glass. What's the N value of glass? It specifically says it on the test, and the reason why is because unless I use a specific term that exists in the book, it's not going to match up. So I need to make sure you know exactly what N value to use. So I will use the 1.53 that's produced on the test. And then it's sine of theta 2. I'm looking for theta 2, so I'll divide this side by 1.53 and figure out what all this stuff equals. Into the calculator, 1.33 sine of 32, close parentheses, divided by 1.53 is 0.4606. And to finish solving for theta, we'll do a sine inverse of that answer. Should get 27.43. That was some number. Then we get 27.43 degrees for theta 2. Any questions there? The only way I really usually get kids to trip up, and I don't always do this, again, I got to write the test. Depends on how I feel the day I write it. Hopefully I'll write it before, well, maybe I should write it after districts, and I'll feel really good. And everyone will be happy, and I'll write really easy tests. I don't know. But the only way I've ever really messed kids up is if I give you one of the angles that's not perpendicular to the surface, not measured from the normal, or I ask for that. That's the other one that'll get you, is I'll ask you for one in the picture that's not the one that the formula gives you. And you just have to pay attention to what surface is. Yeah, you got 90 degrees, it's a complement, so. Mr. Welch always likes compliments. Okay. You got one. I am sure that you guys better understand than necessary why Mr. Welch is a teacher. It's for himself, his jokes. I just need a reason to say them. I don't even need people to laugh. I just need a reason to say them. If I worked in an office, I probably wouldn't have any good ones to say. So anyway, What percentage of light intensity of the light seen in the diagram is seen after it passes through the polarizers? So we're coming from the sun. So over here on this side, we're going to say that our I naught is 1. I'm just going to go with 1. It's 100% of the light is hitting that first polarizer, and it's going to reduce as we go through. Okay, what's the amount of light that makes it into the second session, or that second gap? 0.5. So right here, we're getting 0.5. Now technically it's 0.5 of I1, but I'm just going to run with 0.5 because I1 is 1 by assumption. You might have an actual measurement if you had a device, which they do exist, to measure the light intensity of the light coming from the sun, and then you could actually calculate the watts per square meter that's coming through. We're not doing that. We're just getting a fraction or a ratio that comes through. Okay, so there's my 0.5. If I want to come to this next gap, I have to acknowledge the rotation of the Polaroid I'm coming through. So the formula is that I will equal I naught cosine squared of theta. So for this one, the intensity coming out will equal the intensity before 0.5 times the cosine squared of the Polaroid it just passed through, which is 13. So let's call that I naught. We'll call this I1. We'll call this I2, I3, and I4, just so we can keep track of them. So I'm doing I2 right now. If we type into our calculator 0.5 cosine of 13 parentheses squared, we're going to get 0.475, roughly speaking. And when we come to the next one, it's going to be 0.475 cosine squared of 20 degrees. We're just going to keep multiplying by the cosine squared of the angle that is next. So I'm just going to take in my calculator times cosine of 20 parentheses squared, enter, and then I'm going to times by the cosine of 90 squared. And what do we get? 0. Why do we get 0? Because we got 90 degrees off from its most recent. What this means, you guys remember in the class, I pulled those Polaroids out, and I had 2 that were at 90. I slipped one in the middle that wasn't at 90. But if I had put 2 back to back that were 90 degrees offset, the third one behind it, or the one in front of it, wouldn't matter. Once you get back to back 90s, there's nothing you can do about it. Okay, they will block out all the light. So at any stage, if there's a 90-degree rotation, it completely blocks the light out. As a side note, just because I don't want you to be thrown off when you see weird things happen, but what would happen if it was off by 180 degrees? 180 degrees is equivalent to no rotation, right? Because the lines would be lined up. So if you get an obtuse angle, again, I don't think I'm going to do that here, but the reality is if it was an obtuse angle, you'd use the supplementary angle to use as the actual difference, right? So what's supplementary to 180? 0. If it was 135, what's supplementary to 135? 45. And you say, it's the same as a 45-degree rotation. Because rotating clockwise 135 is the same as rotating counterclockwise 45. It doesn't do any different. At any rate, that's why that came out that way. Otherwise, you just keep calculating. Okay, look at this. We got, you know that feeling when you get goosebumps? Not like the books, but the hair on your arm stand up? Well, it's like that, only different. Actually, the only connection is that your hair would be standing up. They're actually unrelated phenomena, and this is a bad analogy. Okay, so you know how they say opposites attract. Well, it turns out they really do. How strong is the electrostatic attractive force between a single proton and electron that are 3.2 nanometers apart? So this would be a Coulomb's law problem, which is F equals K Q1 Q2 over R squared. K is a constant, 8.988 E9. You guys correct me if I'm wrong on any of this. The charge of an electron and proton are the same number. One's positive, one's negative. Because we're asked how strong the force of attraction is, it doesn't matter whether we apply the negatives or positives. If you gave me a negative answer here, I'm not going to throw a fit. If you give me a positive answer here because you recognize, hey, you just want to know how strong it is, that's fine too. So the strength of an electron's charge is 1.602 E negative 19, and the same is true for a proton, 1.602 E negative 19. That's all divided by the radius squared. The radius is the distance between them, which is 3.2. Nano is E negative what? 9. It looks like the word 9 if you write it out. Nano and 9 are very similar. It's usually a pretty easy one to keep track of. So this would be E negative 9, and that's squared. Plug this in the calculator and get my answer. If I wanted to trip you up or make this a little bit messier, things like asking how far apart should the proton and electron be so that their force of attraction is a certain number. You'd have to algebraically maybe do a little Welch in there to solve it. But otherwise, it's just going to go straight in the calculator. I'll even use a little alpha y equals to make it stack up right. 8.988 E. Is it E9 or E negative? It's E9, isn't it?
Yeah.
E9. I get all these positives, negatives mixed up. And then I'm going to go 1.602 E negative 19 times 1.602 E negative 19, all divided by, parentheses, 3.2 E negative 9, parentheses, squared. Don't forget to square. And I get 2.25 E negative 11. 2.25 E negative 11. And the unit should be newtons because it is a force. That's a pretty small force, but remember, electrons, protons are babies. Go guys.
Why are we using a 3.2? It's supposed to be a radius.
So when we talk about radius, this is a good question. It's the same as asking about the radius of planetary movement. If you talk about the two objects, right? Here's my positive, here's my negative. Don't think of it as, so a radius is a circle, and typically things like this, like planets, are going to orbit each other. And so when we talk about the actual radius, if we think about it as an orbital dill, the radius is the distance between them. So it's written with that perspective of orbiting behaviors, not in the perspective of, if it was a distance question, we would say d. And if we wanted to say it was half the distance between them, we would say half d. We would use an r to represent that. Good question, though. All right, time for break. Here's some good jokes. Oh, these are good. How do you currently feel? Current, it's measured in amps. So, all right. And watt, did the electrician say when he electrocuted himself? It hurts a lot. That's funny. Okay, power rating is needed to use, minimum power rating to use a resistor in a circuit hooked up to 120 volts, has a device, has a resistance of 13 ohms. So a couple things. V, we've got 120, and we've got an R of 13 ohms. Right now, I know V equals IR, that's Ohm's law. I could use that to determine I if I want to know, but we're really asking for power rating. Power is by definition IV. That's the formula we use for it. You can replace like the I with V over R. There are different versions of this formula. My my basic always do the same approach is just find your missing variable with Ohm's law. So I would just go 120 equals I times 13. That's going to give me an I value of 120 over 13. Roughly 9.23. And then I can use that in my power formula. 9.23 times 120. And this will be something in watts. So if we take our calculator out, We're going to times that by 120 and get 1107. With this being a number that we're saying what's the minimum, I'm going to definitely want to make sure that I'm not underwhelming. If I have it rated at 1107 and we're putting more power in than that, it's going to burn up the resistor or the component. So I'm going to round up to get a higher number. Say I need to be above this number. So I'm going to call that 1108 or 1110, either way. So 1108 watts. Let's go. Are we on the last page now? Oh, we are so good. All right, we got to determine the resistance in the circuit. Looks like we've got, 5 resistors in there? Okay, when we're working resistors and combining them, remember we're going from the most complex to the simplest. And so, we want to work our way, again, complex to simple. Okay, so when we're combining these, going the most layered, deep inside of things to the most simple. So when I'm working here, I'm going to look at this big complex chunk and try to break it down. When resistors are back to back in a series connection, like the 4 and the 3, how do those get combined? That's just a simple addition. So this now becomes a 7 ohm resistor. Okay. Now the 7, the 5, and the other 7 are all similarly embedded in that parallel connection. So then I could take all of this chunk and go work on it. How am I going to add the 7, the 5, and the other 7?
1 over.
Yep. This is that parallel where we do 1 over, 1 over, 1 over, all raised to the negative 1. So we have to add these in that pattern. Grab my calculator. 1 over 7 plus 1 over 5 plus 1 over 7. All raised to the inverse is going to be 2.059 ohms. That is for this parallel connection. Now we want to go through and get the 8 combined with our 2.05. And because those are in series, right, just straight line connection, I can just add them and get 10.059 or 10.06, 10.1, whatever number you're going to choose to round up in ohms. Again, the most common, boneheaded thing I take points off for over and over again is we're not putting units in problems. So please make sure that you do. Bless you.
Thanks.
All right, Katie and I believe in always having a positive attitude. If Katie and her positive cheerleader charge is moving west through a magnetic field that is pointed south, which way will she be deflected by the electromagnetic force? This is not supposed to be complicated. This is simply a right-hand rule problem. You don't even have to make a calculation. You just have to know which direction to point. So I'm going to give myself a little bit of a bearing here. Okay, I'm going to say this is north, and this is east, right? West and south. The other directions that exist in this framework, if you think of yourself, if you're pointing north, south, east, and west, the other direction that you could describe would be up and down. I want you to think about it, Nolan, and anybody else. If you're thinking north, south, east, west, that's like right, left, forward, back. The only other direction to go on the earth is up and down. Okay? So that's how I would typically describe this because of the framework you were given. You could say into the page and out of the page, and you could do it all on the paper. But my brain, when I'm thinking about this physically in space, I would want to use that spatial awareness. Now, here's what I'll also say. Okay? There's nothing wrong with you guys sitting in the room and actually orienting your body to the cardinal directions. We know that we're in the East Hall, right? So we kind of okay, South Hills, East Hall, where's the north there? There's west that way. Okay. I know where stuff's at now. All right. So in this situation, we have Katie with her positive cheerleader energy. So we're going to call her a positive charge. Okay. Is moving west. So in this situation, it is moving west. Okay. That's her velocity. And the magnetic field is pointed south. So our magnetic field is pointed south. Okay. The question is, which way will she be deflected? Okay. Well, here's what I'm going to do. I am actually going to point myself west. Physically make my body point to the west, which would be the front of the classroom. Okay. My fingers are going to point in the direction of velocity. I am going to curl my fingers in the direction of the magnetic field. Which way is the magnetic field pointed? South, which would be towards the South Hills or towards the South Hall. So imagine going down to the Commons, and on your way, when you hit the foyer, you take a left. Okay, which way does your thumb naturally point? Up. Which makes sense because cheerleaders do all the tossing and tumbling. Right? This is supposed to be an easy question. So the answer would be up. She's deflected upward off the ground. So again, if Katie actually was a positive charged particle running down the hall and there's a left pointing magnetic field, she would take off and leave the ground. Okay? If you draw a picture on here, or there's a picture drawn on here, and your best way to describe it is in and out of the page, that's fine. What I would recommend is that you be very descriptive when it comes to direction. If you draw an arrow on the page, that does not help. Because I can't tell if you're trying to draw an arrow into the page, like there's an angle to just tell me direction. Okay. Last question. We have a bonus problem. Completing a ray diagram for a diverging lens. These are a little bit harder because it's the same three rays, but they're drawn differently because of the diverging nature of the ray. Let's go blue. Let's go with light. Okay. Again, the measurements that are drawn on your paper, it's 4 centimeter gap to the first focus and then 2 centimeters on each side. The first ray goes out parallel. What does it do once it hits the dotted line? It is going to extend out from the near focus. So it ends up looking like that. I'm going to tweak the drawing here just a little bit. So bear with me. Can anyone tell why I did a dotted line there?
Because it's not actually.
Yeah, the light's not actually passing in that pathway. It just appears to be coming from that direction. View. Okay. Next ray. Okay, this next ray is going to go as if it was going to hit the far focus. Right? That's where we're aiming. But what does it do instead? Comes out parallel. And again, if I'm drawing, it looks like the light is targeting that focus, but it also looks as if it's coming out from a parallel path. So the hard part with this is really the fact that, and you could draw these solid. You don't have to have dotted lines. I'm just distinguishing between where the light actually goes and where it appears to be coming from. And the third and final ray is always straight through the center of the lens. Like that. We can see that on the right, these three rays are diverging. This is why it's called a diverging lens. They're all spreading out, staying away from each other. Well, where is the actual image going to show up? It's going to show up right around here, where the three lines all intersect. So we're expecting an answer right around there. Okay. It's a little bit complicated because, again, we bend the rays. They don't bend where we expected them to. The other one is so easy because it all kind of converges to that single spot. This one, they're diverging from a single spot, and you have to backtrack to find it. Okay. That's it, guys. Let me know what you need help with. We're taking the test over 2 days. So if you need 2 days,